The Great Pyramid, Khufu's pyramid, is like a solution of the squaring of the circle. And the height of the pyramid is now the height of the Earth's polar radius.
Oh, wow.
So, and I mean, I'm talking about very, very close, like within a few dozen or maybe 100 or 200 feet maximum. The problem is that the Earth itself is not a perfectly rigid body, but it has a little bit of give to it, a little bit of plasticity to it, so, or elasticity to it. So, you know, if you measure the Earth to that kind of precision, to where you're measuring an axis of the Earth within a few feet, you're going to be lucky to get the same exact number every time, because things are moving. I mean, think about just a big earthquake. You might have a whole section of the tectonic plate that shifts up or down by 6, 8, 10 feet. So the point is that I'm getting at is within a very, very small margin of error, you are literally, you can say that, yeah, the pyramid is a model of the northern hemisphere. Now I build digital models.
Yeah.
And of course, those digital models can be extremely precise. You might put exact numbers into those digital models, and I can program it where I'm like, there's no point in programming it to 1,000th of an inch. That would be meaningless in building a house. So what I do is I set it up to a 16th. So if I divide 1 by 16, that's 0.0625. So I'll set it up so it's accurate within 0.0625 of an inch.
Right.
And because I know that in the field, we ain't even working that precise.
Yeah.
You know, typically our steel tapes, our smallest unit on a steel tape, a measuring tape, is 1/16 of an inch. Yeah. But when you're framing a house, you don't do the same degree of precision as if you're building a fine piece of furniture, right? So, yeah, so you kind of have to determine, okay, what's my allowable margin of error? Now, the difference between the idealized model and the actual structure when it's finished, its accuracy is really a measure of the level of craftsmanship. Really good craftsmen, like my team, are top notch. So we can lay out a house that's, 50 feet wide, and it will be accurate. When you run those diagonals from one side to the other, it'll be accurate within 1/8 of an inch, which is
which would be a 1.25% margin error.
Yeah, so 1 divided by 8 is 0.125 in. But if you've ever studied calculus, you know that the basic idea, the fundamental idea of calculus, is that of a limit. And a limit is something which you can determine with a degree of precision. But, like, for example, if you're trying to find a line that's tangent to a hyperbolic curve, it's only going to be 1 point. But how close do you, now I could say a hyperbolic or an elliptical curve, because all planets they're all, basically all orbits are ellipses of a greater or lesser degree of eccentricity. We don't find any orbits that are perfect circles, right? Just like when we look at getting back to the moon, we have the perigee and the apogee. The perigee is the closest, and you can fact check me on this. I think perigee, Darren, we're looking at about 221,000 miles. And at apogee, I think we're looking at about 252,000 miles. That is the difference between the moon's closest and the moon's furthest distance from the Earth.
Mm-hmm.
Is it close to 200? Is its perigee close to 221?
Oh boy, I'm fact checking. I'm looking at.
Darren looks at that.
So while Darren is looking at that,
I want to bring something up quickly, because I'll never forget when Darren asked you a question. It's had me thinking about this ever since. When on our earlier podcasts, does that template that you talk about, like, is that unique for each solar system? It seems to be like built into this, our solar system maybe only, and another system way over there has a completely different template.
Well, given this, okay, the the positions, the architecture of the solar system is appearing to me like it's whatever, it's optimum for the generation and evolution of higher sentient life. Because, for example, I think if you look in the models of exobiology, and I definitely lean in that direction, I think the evidence is becoming overwhelming that life was actually, the precursors to life anyway, were introduced from outside into the Earth system at the appropriate time when the temperature and the ratio of water to land and all of these other factors are optimum. Life is seeded. Now, of course, that gets us into the question of that we won't necessarily get to here, whether the theory of panspermia, that life is seeded, for example, throughout the universe. And I think there's some interesting new research along those lines showing the importance of organized plasmoid systems in that, being actually the way that these microscopic precursors of life could be channeled through space. But then there's also the probability of things like comets, even asteroids, having the raw materials of life being delivered to Earth. Now, after the creation of the solar system, and however that occurs, if you take the nebular hypothesis, you have the sun consolidating as the center of the system, the center of mass of the whole system, and then all of the outer planets are gravitationally cohering based upon their distance from the sun. And I mean, there's so many mysteries and it's so complicated, I'm not going to even attempt to get into that, explaining the origin of the angular momentum of the solar system. Okay, is that's that's a mystery. I don't think anybody's really solved that, why everything is spinning, and it's spinning in the same direction, right? And rotating and spinning, rotating and revolving in the same direction.
Except for the moon.
What?
Except Venus?
Except, well, Venus is revolving in the same direction, but it's rotating in the opposite direction. And damn it, I wish I had here I am totally unprepared. If I don't, I have, when I've got a globe, I can demonstrate this, but I'll try to demonstrate it anyway.
Well, before you do that, so in 2021, the closest perigee on December 4th was 221,702 miles, and the apogee on May 11th was 252,595 miles.
One more thing. The diameter of the sun, generally, and that's you can quibble about, what's the sun's diameter. Problem is the sun doesn't have a solid surface like the Earth that you can measure. You've got the chromosphere. Do you include the chromosphere? Just like if you were going to measure the Earth, presumably you would measure the solid surface, but you could include the atmosphere, right?
Yeah.
But the sun's is much more complicated than that. So, if you include the chromosphere, it's closer to 865,000. But if you don't include it, then it's closer to 864,000 miles. And that's, I think, the traditional number that's been associated with the sun, 860, which is very close to the sun's actual diameter. Now, of course, what happens when you divide 864 by 2? You get 432,000.
The moon has the weird thing where it's 27.3% the size of the Earth, and it's 27.3 days of rotation.
Mm-hmm.
And the Earth is 365% the size of the moon, and it takes 365.25 days to do a rotation. And that's all by like NASA's own numbers. So to me, it's either it got made, it's intelligent design, or the numbers were like made up to fit some occult.
Rather. And you could also point out that now this is it changes all the time, right? Because the moons, when you talk about the moon's orbital velocity, that's going to be taken relative to the Earth. That's going to be different at perigee than it is at apogee, right? But you can say, and just like there's going to be a certain point within the moon's orbit where it is moving precisely in 1 hour, in one of our hours, a distance equal to its own diameter.
Man.
That's interesting, isn't it? So it is when you get into it, you know. Okay, so here, yeah, I mean, this is where my mind starts to just sort of boggle into incoherence. Is that, well, you brought it up, Graham? I mean, or Darren? I mean, is this intelligent design, or is it out of all possible world systems, this happens to be unique? And by whatever cosmic accident, it's just the right arrangement here in order for us to be sitting here having this StreamYard meeting tonight.
Well, I would offer you one more, and that it could be like some weird law that just like, because if gravity doesn't work the way we think it does, and it's, you know, we've got other pretty smart people who thought it was magnetism, and some other pretty smart people who think it's electric, but maybe it's just held in place by these ratios somehow. It's some weird law that we don't understand. Is that a possibility?
Well, if you start talking weird laws that we don't understand, I suppose we could say, yeah, that's a possibility. I don't know. I don't know. I don't know. And there's Malcolm calling me. I should have turned this off. I'm sure he's got some big news about the plasma technology developments.
Want to bring him on the show? Then?
Here's a question from the chats. I wanna. This is a pretty good one from Mike. Mike, that's probably Wix. The sun also rotates around its axis in the same time it takes the moon to go around the Earth.
Yeah, that's about right. I'm pretty sure that's about. You could, if you have it all pulled up there, Darren, I bet you can see the sun's rotational period. Interestingly, the sun's rotation, like it varies depending on latitude from the solar equator. But I think overall, you said his name is Mike.
Yeah, I'm pretty sure Mike UU is our buddy Mike Wicks. He's been on a couple of trips. You would know him to see him for sure. I might have just probably
once in about 27 days.
And of course, the rotational period of the moon around the Earth is 27.3 or 27 or something like that.
So there again, we've got that little bit of discrepancy, but and 27 is 1/4 of 108. So 27 times 4 is 108.
Nice.
And 108 times 4 is 432. So
have you looked into the Tycho stuff at all? Like, so let me just put it to you this way. Is it crazy to think that the Earth and the moon could be at the middle of this thing still? Is that like definitely out of the question? Because I've seen some evidence that has me leaning in the other direction. And I'm going to this conference this summer to look at this Tycho's thing because they seem to explain some things and predict some things that we have to come up with like retrogrades and stuff for. And maybe those make more sense to you than they do to me. But, you know, so I'll present it to you that way. Is it out of the question that the Earth is at the center of this thing?
In other words, geocentric?
Yes.
No, well,
is that what you're saying?
Geocentric in a binary system with Mars in the sun, though, Darren, I think is the key.
Yeah, that's what it is. Yeah, right. There's more to it than that.
Well, I haven't looked into it. I haven't at this point encountered anything that would make me question the heliocentric, and I can explain retrograde motion relatively easy, or at least I can demonstrate it. And yeah.
I'll send you the book. And
what's the name of the book?
The Tychos model, I think. I've got it on PDF. I'll email it to you.
Yeah, actually.
I think we might have showed you on one of the trips because there's a few people that have been with us that have loved, like, they're really into this whole model. And,
yes, I don't send me the book. I have it. Okay. And from my scholarship days, I recall that Tycho was actually pronounced Tico.
Yeah. I can't get away from Tycho.
It's hard, right? You want to say Tycho.
Yeah.
Um, yeah, I remember when I was a kid, I was maybe 6 years old, just learning to read. Let's define the plane of the ecliptic then. I just defined it. It's the plane that's swept out by the Earth and the Sun. It's if you were to connect the center of the Sun to the center of the Earth, that line would lie in the plane of the ecliptic. And then all the other bodies in the solar system are defined, their orbital elements are defined relative to that plane, the plane of Earth's orbit around the sun. Right? So all of the other planets lie within the zone, but none of them lie exactly. Their orbits are all tilted, and I don't know those off the top of my head. I do know that off my top of my head that the moon's orbit is tilted 5.145 degrees off of the plane of the ecliptic, right? 5.145. So what that means is that for half of its orbit around the Earth, it's above the plane of the ecliptic, and for half of its orbit, it's 5.145 degrees below the plane of the ecliptic. And there is that intersection point that's in its own way kind of analogous to the intersection of Earth's equator, the equatorial plane, and the plane of the ecliptic. And just as because of Earth's precessional motion, like this, the intersection of the Earth's equatorial plane and the plane of the ecliptic is moving basically at the same rate, 50 seconds of arc per year of this. Okay, so at this point, it would be a good idea to pull up the graphic and we can actually see. Is that you do? There we go. So here we see the moon is above. Here's the nodal point where the moon is crossing the plane of the ecliptic. And it's going down, coming back around, and coming up here again. Now it's crossing from southern latitude into the northern celestial latitude and spends half of its time. And so an eclipse can only happen when the moon is at one of the nodes where the two planes are intersecting. The more we learn about the moon, the Mascons are particularly interesting. And what the hell are they? The one-to-one spin orbit coupling, that's interesting. The overall low density is interesting. The slow decay of seismic vibrations, lunar transient phenomena.
What's a Mascon? It sounds like a COVID thing.
It sounds like what?
A COVID thing, Mascon, Mascon.
Stands for mass concentration.
Okay.
And mass concentration is are these extraordinarily dense zones under the Maria that are so they're so strong that they actually deflect. In the early days, they would when the lunar orbiters would fly over a Mascon, they would actually be deflected in their orbit because of this something really strong under the surface of the center of the Mascon.
Have they mapped those? Do they have you seen a map of them? Do they look does it look fake or organic?
No. I've mapped them. I mean, I haven't mapped them, but I have showing the maps of the Mascons. I've got it in my 329 slideshow, right? Okay, so
are they all on the same side?
Are they all on the same? Most of them are on the near side because most of the Mascons are on the near side, right? There's one Mascon, I think, on the moon's far side. And I'm trying to remember if there's a Mascon. Most of the Maria have these Mascons under them. And again, I wasn't really necessarily prepared to get into that. But if you wanted to, I could get it set up. We could take a little break or something, and then we could come back to that. But we were going to focus more on the eclipse. Where am I here? Come on, damn it. Slide 29, 30. Okay, do you want to, since I've got it right here, you want to do share screen?
Yep.
Yeah, let's do it.
Okay. So this is a lunar gravity map, and the contour lines show the gravity strength above the mean value of moon in units of 100 milligals.
I think you got to click on it still. We
Oh.
don't see it yet. Yeah.
Can you see it now?
No.
I can't see. You got to click present again.
Oh, right. Of course. Yeah, sorry. Share screen. Share screen. Should be the same window, but I got to select it again. Screen 2. Yeah, there we go. You getting it now?
Yep, we got it.
Okay, so these are these extremely dense regions underlying the lunar surface, mass concentrations. And this is the near side Maria, which are the big, the seas, the dark blotches. When we look at the moon and we see the man in the moon face, that's because of the Maria that we're seeing, right? So the Maria, all of the near side Maria have these gigantic, we don't know how big they are, but whatever they are, they're extremely massive and extremely dense. And that's an anomaly. The reason it's an anomaly is because they are so much more dense than the surrounding material would be implied, that they should have eons ago sunk to the center of the moon. Just like if you put a little lead pellet on the top of a surface of a bowl of Jello, what's going to happen? It's not going to drop. It, of course, depends on the viscosity. You put that lead pellet, and if it's water, it's going to go really fast to the bottom of the bowl. If it's
yogurt,
it's going to go right. If it's Jello, it may take a couple hours, but it's going to sink through. Now if you took a green pea and put on there, it probably wouldn't sink, right? But the lead pellet would sink.
So is this a density then, or what is that brown dot then?
It's density. That's exactly what it is. And let's see here if I got something. So here's another, vertical acceleration at the lunar surface for the LP165P gravity field. Acceleration of the radial component at the lunar surface sphere with radius 1738.0 kilometers. So 1738 kilometers times 1.62. Okay, so the near side on the left includes coefficient to degrees and order 110. We don't need to explain all that, but this is again showing these large density anomalies. Here we can look at this quote: "The discovery by Muller and Sogren of Mascons in the moon is of great interest. My investigations allow a calculation to be made of the size and depth of the Mascons in terms of the size of the mare formed by low velocity impact of an iron meteorite." Now, the problem with that theory early on is that at whatever velocity you bring that collision to occur between meteorite and the lunar, the meteorite is going to basically vaporize. So I am currently completing an analysis of penetration and cratering of concrete and soils by steel projectiles. He goes on, let's see here.
Yeah, but even if it vaporizes, wouldn't it just maybe push or squash it all together to concentrate the mass somewhere?
Probably. So these results suggest that the lava-filled Maria were formed when very large iron objects struck the surface of the moon at a velocity so low that there was no immediate fracture of the object. The depth of an impact crater measured to the bottom of the shattered material in the crater is approximately 1/4 of the crater diameter, right? That's a good rule of thumb that you can use. Now, okay, so this means that if the Maria are filled craters, the depth of Imbrium should be about 300 kilometers. That's 180 miles, but it sure ain't. In fact, it ain't. It's not any deeper than about 3 or 4 miles. And the depth of Humorum was about 100 kilometers, which would be about 62 miles. If the Mascons are deeper, as I suggest, then they must also be more massive to produce the observed gravity anomalies. So in other words, the deeper they are, the more massive they have to have that corresponding deflection of something flying over it. Now, if they had all sunk to the center, right,
Then
then
it'd
there'd
be
be
equal.
an anomaly. It's, you're not going to have it. So it has to be close to the center. The closer to the center, the less
Or the
the
surface.
closer to the surface. Thank you. Closer to the surface, the less the mass. Let's keep going here. So here, yeah, Muller and Sogren. This is isostasy on the moon. This is all research done back in the Apollo days. Muller and Sogren have performed the astonishing feat of providing a relatively detailed, though preliminary, gravimetry of much of the front surface of the moon. The data from which they worked is in no sense marginal. The perturbations of the orbiter satellites which they used are so large as to have been an operational nuisance before they were understood. The interpretation suggested to Muller and Sogren by the papers of H.C. Harold, that would be Harold C. Urey, and tentatively adopted by them, attributes the mass excesses in the Mare regions to mass concentrations, perhaps remnants of colliding asteroids, on the order of 100 kilometers in diameter, buried under the lunar surface. On the other hand, both observation and experiment indicate that impact at normal meteor velocities leads to the scattering of the impacting mass as a result of shattering and vaporization. Even if it is supposed that the circular maria were made by bodies already in orbit around the Earth, and hence having relative velocities of only a few kilometers per second, there remains a difficulty in supporting the mass. The pressure exerted by such a body on its base would be the order of 8 kilobars, which is 110,000 pounds per square inch, and this exceeds the crushing strength of granite. It is reasonable that a mass of this kind would crush its way to the center of the effing moon. Okay?
Makes sense.
Yeah. So Muller and Sogren have concluded that there are very massive objects in certain locations at the surface of the moon. Now, we see these are anomalies. These are things that raise some very interesting questions. So yeah, if the Mare Imbrium situation is taken as a prime example, because it exhibits a maximum effect, we come to the conclusion that the viscosity of the moon must be higher than that of the Earth by a factor of 10 to the fourth.
So that'd be, whoa.
Difficulties we're running into here. And it is difficult to devise a lunar history which provides the low temperature required to account for the lack of isostasy and the low electrical conductivity, and at the same time for melting processes required to produce the basaltic material on the surface of the moon. So here you have these huge maria, the 100 to 300 kilometers in diameter. They're extremely shallow relative to what theoretical calculations suggest their depth should be. And then right at the center of them, you have these enormously dense masses of something.
So it sounds like it was already dense mass, and it just whatever impacted it couldn't go down any further because it was so dense. So it has to be shallow.
So, but see, the density is not a uniform thing over the surface. Then you have to assume that if the density was already there, then all of the impacts that produced the maria had to have impacted directly into that anomalous dense area. In other words, go back to the lunar map we were looking at. So,
are all the craters that have the same ratio of depth to length?
No, but what they do have is they have a limit in depth. Well, yes, because it's tidally locked to us, because the crust apparently is so rigid that yeah, I'll show that in just a second. I think I can kind of explain that. At one time, it was naively believed that Mascons are remnants of the dense projectiles responsible for the excavation of the basins, right? But it was soon realized that they would have been totally vaporized. Furthermore, the largest Mascons only occur in those basins which were filled with Mare basalt. But if mascons are simply layers of Mare basalt lying on top of low-density crust, how is this excess mass brought to the surface in the first place? Well, if a planet is in isostatic equilibrium, the overburden pressure will be constant at any given distance from the center of the planet. Terrestrial continents are much thicker than the oceanic crust on Earth simply because granitic type rocks have lower densities than oceanic basalt. So, yeah, you can see here, this is just one of the anomalous things that are difficult to explain that we can add to the mystery of the moon. Let me see if I can. There was one. Yeah, here we go. Even though we have computed both masses and depths for the largest mascons, nevertheless, our present quantitative data require further refinements. One may easily compute approximate masses from an assumed depth, say, such as 50 kilometers, which would be about 30 miles. The Mare Imbrium mascon yields numbers on the order of 20 times 10 to the 6th minus 6th lunar masses. So that would be about one over 20 with 6 zeros. A spherical nickel iron object about 100 kilometers or 60 miles in diameter would be a rough equivalent. So if this thing was 30 miles under the surface, it would be the equivalent to an nickel iron object.
Which would be one of the heavier, would that be one of the heavier?
The size of a city.
Well, yeah, except you got to figure this thing is, this thing, but if you picture this is a solid object. It's, if you had a spherical object, it would be 60 miles in diameter. However, NASA's budget's being cut way back in order to be able to send 60 billion over to Ukraine. Literally, that's where what's happening. There's money is being taken from all these other places. We can't afford to complete that program now because we have to send another 60 billion down the rat hole of the Ukraine war and the rest of it that it's probably going also to continue
climate change and military
all of the bullshit. Yeah, all of the bullshit that there's completely wasting. Well, yeah, I mean, look at the Inflation Reduction Act has billions and billions of dollars to address a non-existent climate crisis. I'm sure that, the best case scenarios in the aftermath of that orgy of pointless spending, we are able to, salvage some use or value out of it. But for the most part, it's just money down a gigantic toilet is what it is. So let me then, we'll stop share again, and I'm going to go back so we can get to, go back to the question of eclipses. We kind of we digressed there, but I hope it was an interesting digression.
Oh, yeah.
It was.
Okay, good. Yeah, so I'm flying back to my ancient observatories here. I got to tell you, man, I got some interesting stuff in this program here that I've decided that we've got to have more. People have been bugging me for years, and I've been a little bit wary about releasing this prematurely. And then when I found out we were going to be doing the Artemis program, I thought, well, okay, so I'll do a 3-stage disclosure coordinated with the Artemis missions. And then now with the question as to whether the Artemis missions will proceed as planned, I don't know. Tell you what, though, we got to get that Biden administration out of there down here, and you guys need to get Trudeau out from up there.
That's right. It seems to be trending in that direction.
I hope so. Okay. So now I'm going to go back to screen share, share screen, screen 2, allow. All right. So for anybody who wants to do this kind of research, this is one of the best, the work of Alexander Thom. And this is his work. He spent God, decades. He was a surveyor, and he spent decades. He was he was also an engineer who was also an expert in surveying, and so he spent decades surveying what he calls the megalithic lunar observatories, which shows, I mean, his work along with the work of many others at this point now, this is from 1971, as you can see. There were many people in the ancient world that were obsessively watching the moon and observing the motion of the moon. And then he uses, like here's Stonehenge. Now this is from, not from Tom's work, but Tom's is the essential work that anyone wanting to dive into this should probably start with. But so this is the lineup showing the alignments of Stonehenge, and you can see here you've got most southerly moonrise. You've got the sunrise in there. Over here is most northerly moonset and most southerly moonrise there. And you've got, it's primarily solar, but they've also got the lunar alignments in it. Let's see here. If we go to the next one, let's see. Here we go. Yeah, here. This is the one I was looking for. So here, the red line is the midsummer sunrise, and it swings back and forth like that, right? Now, that angle of swing between the most northerly and most southerly is going to be pretty well fixed with respect to sunrise. But with respect to the moon, because of the fact of that 5.145 degree tilt, it actually affects the limits of the moon's rising and setting. So there's a minor rising. So in other words, imagine if the sun one year would come to the north and pause, shift back to the south, but the next year would move a little further on the horizon. So now that would be the major rising point and the minor right. Well, so this is what happens with the moon. There's a minor and there's a major. But in order to complete that whole cycle, that's where the 18.6 years comes in. So from Stonehenge, you can see that, oh, here we go. Look at over here. Here's your major midsummer moonrise, and here's your minor midsummer moonrise. Here's your midwinter, and here's your midwinter moon set, major and minor.